Oh, those are those Chinese green tea sticks or something, are they?
No.
That's Japanese British thing.
Yeah.
That's not the thing. Who gave me that last time?
Jerry.
Jerry?
Jerry gave
Wait,
me.
you... Don't confuse me, you're Jerry. Okay. Be nice, Jerry. Don't call people stupid unless they are stupid. Okay. IV characteristics. We can write that down. I'll explain this word, Sean, don't worry. Dorks. That's all I can say. Dorks. Alright, you got that? Does anybody know the meaning of this word characteristics? No. No, I know you don't, Sean, because you looked shocked when you saw it. Does anyone?
Properties.
Properties, yeah, properties would be a good synonym for this.
Speciality.
Properties. And the IV here is standing for current and voltage. So basically, it's a way of saying current voltage property. Or rather, it's going to be current voltage relationship. What's the behavior between the two? Okay, so let's start anyway. So this circuit, quite simple, it's quite important. And I'll explain why it's important and why it's useful, but it is actually a very important circuit. Now, just to recap, Jerry, my friend, my good friend Jerry, what does the V stand for? What's this called? Now, just Jerry, the V, what is this? Oh, come on, Jerry, I think you know this. No, Sean, don't look, because you're going to be next. Do you know, Jerry?
I don't know.
No. Sean, what's the V called?
V is V. Ah, I know. One of it.
Sorry, this is what happens. Like, do you know what it is? No. Teacher, I know now. What is it, Jerry? Voltmeter, correct. Voltmeter. And 2. What's the A? Okay, we don't quite remember. Bruce, what's the OR? Yes? Oh, you know this one, Sean? Resistor. And lastly, Monica, what's this symbol here for? Yeah, resistor. You can change the resistance. Yeah. And then, Andrew, what is this? Battery. 2 cells. Yeah. So it's a simple circuit. I want you to draw this. It's a circuit you need to know for the exam. Okay? Oh, you can't quite see it. It's blurry. Oh my goodness, this doesn't have the switch. It's so dangerous. Yes. Sean's right, this circuit is missing a switch. This circuit. If you like, for safety, you can put a switch on the side here. Yeah, okay, then no switch necessary.
Why do you need a switch?
Well, suppose your friend in the lab is being electrocuted by the battery. It would be nice to turn the circuit off. You know? Okay, did you draw that? Yeah. Okay, let's have a look at why this is important. Okay, so my pen, just need to turn my pen on. Come on. There you go. Alright. We got juice. Nearly got juice. Give it a moment. Give it a moment. There we go. We got juice. Okay. On the bottom we had the variable resistor, was it? Let's just check. And on the top we have the fixed resistor. Okay. So here, I'll just draw this again so I can explain it. Ammeter was on the right.
Right.
Okay. Not that it really matters. Yeah. It's the same. Oh, and battery here. And here, Sean.
Voltmeter.
Very good. Okay. Right, so let's have a look at what's happening in this circuit. And this is an OR, we'll say, resistor. So this current will flow this way. Through here, through here, through here, 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 and here. And this resistor we can change. Let's give it a different letter. Let's just call it, I don't know, small r. Okay. Will this voltage change? No, this could be like 9-volt battery. So we'll call the voltage here E. Yeah. Now, what's the voltage here? Well, the voltage here is whatever is on the voltmeter, which we'll call V. And the voltage here, do we know it? No, we don't. We know the OR though, and we can use this VI-OR. So we can say the voltage here would be I-OR.
Yes.
Yeah? We know that I-OR plus V should equal E. Yeah? Now, what happens if I was to make this OR bigger? Then this would become bigger, and what would happen here? Smaller. So in other words, the job of this is to change the voltage here. And as the voltage changes, what will happen is you'll see this will also change as well. So in this way, you can see how the current changes for different voltages. In other words, you can make a table of different values of voltage and its value of current for this resistor. Do you understand?
Yes.
Now, there is actually an easier way to do it, but it's more expensive. You could have something like this. Resistor, current, ammeter, and here you can have something called a variable voltage source. In other words, you can buy a machine and you can decide how much voltage you want to provide. You just turn the dial, 9 volts, 8 volts. Now, I think you might not remember this, might be a little bit too young to remember, but I remember that you used to be able to buy this little plug you put into the wall, and at the end of it was like 8 or 9 different connections. So you could put one in your phone, one in your Game Boy, one in whatever. It was a little plug and it had many different connections at the end for different electrical appliances. But it had a switch on it where you can change the voltage from like 1 to 12 volts. So this actually is a variable voltage supply. It's been years since I've seen one of these, because there's not really a need for it anymore, since everything kind of is powered by a USB cable. Everybody's connection is kind of the same now. But anyways, you can buy these, but they're kind of expensive because you can change the voltage, you know. So the purpose here is just so you can see different V's and different I's. And I've already done that. So here's an example. I decrease the voltage from 10 to 1, and I measure the current, and I see the current decreases from 20 to 2. Yeah. Let us draw this. Now, which should we put on the X and which should we put on the Y? So what goes on the X?
V.
The V. Why?
We can change the V.
Very good. The V is what we can change, so that goes on the X. And on the Y? I. Yeah. Which is amps here. Okay. I'll give you a minute. I want you to draw this carefully, please, and see what shape you get. Ah, come on, it's not going to kill you. I'm sure it'll be a beautiful picture. Drawn, Lee? Ah, come on, put some effort into drawing it. At least reasonably accurately. Sorry. Yeah. Did you draw it, Sean? Let's see, please. Good. Did you write the units on X and Y? Yeah. Draw that? Okay, let's have a look at the graph. Yep. What's wrong? Have you drawn it? I'll give you 3 sips of coffee. This is the first sip. Ah, yeah. All drawn over here? Yeah. What shape did you get? What shape?
Linear.
Yeah, linear. Yeah. Perfectly linear? Perfectly linear? Yeah. Yeah.
Yeah.
Yeah. So let me just draw this. Oh, I need 2 more sips. That was the second one, Monica. This is the third one. Right. First, voltage. Oh, what's another name for voltage, by the way? Potential difference. So potential difference in volts and current in amps. What's my first voltage? 10. And what happens next? Decrease by 1?
Yes.
Until?
1.
And my current starts at and decreases
2.
each time?
Yes.
Okay. Now, just so you know, in the exam, they sometimes ask you to make this graph, so it's not so difficult. But to get full marks, I want to show you, make sure you have everything correct on the graph. Okay. Let's see. So the title is current against or versus, voltage. And this is example. The x-axis is potential difference in volts. I use the slash to represent the unit. The y-axis is current in amps. And you all should have a graph that looks like this. Let me shrink it a little bit. Yep. Whoops. So it looks like a straight line. Okay, and that's important. This is an important type of graph in physics and in electricity. This graph is called the IV characteristics of a resistor. So actually, the name of the lesson was IV characteristics, and now I'm telling you what that is. The IV characteristics is simply just the graph of the I and the V for the resistor. As you change the V, how does the I change? So the IV characteristics of a resistor is a plot of current running through it against the voltage around it. When a power source, when a power source provides a change in voltage, a varying voltage, this is the IV characteristics. So the question might just simply say in the exam, draw the IV characteristic plot. Okay. No. No. Has anybody heard of this or seen this before? Have you heard it called IV characteristics though? Yeah? No.
Never.
Never. Never heard of this. Mm-hmm. You understand it though? Yeah.
I learned it before, but I never seen English.
But I knew that because I knew you studied in Chinese.
I didn't.
No, you didn't. No. I'd be surprised if you studied in Chinese.
No, I never draw the electricity.
Okay. Continue?
Yes.
Yep. Right. So, you notice that this graph looks like the straight line. And in fact, that's a law. Now, before I continue, this slide comes with a warning. Warning. Some of you were told in high school that Ohm's law is V equals I or.
Yes.
This is false. This actually isn't exactly what Ohm's law is. This is of all the things in physics that you might learn at high school, 99% of it's going to be right. Sometimes what you're told is not right on purpose, just to make the understanding simpler. And sometimes you're just told something which is simply wrong. And this is an example, and it's only one example. I don't think there are other examples where you're told something in high school that is wrong. This is not actually Ohm's law at all, because there's nothing special here. This just comes from the triangle. Okay, so this is not actually Ohm's law. So that's my warning. And in fact, even some teachers would not know this, that this is not Ohm's law. So what exactly is Ohm's law? And you need to know this, and you need to know this for the exam. You think you know it exactly? What is it? That's it. With close enough. Ohm's law says, for some materials at low voltage and low current and at a constant temperature, the IV characteristic graph will be linear. Yeah, so what Ohms said was, for some materials, if the V and the I are small, then this graph will be linear. That's Ohm's law. IV characteristic graph is linear. But it's not even really a law. It's kind of a fake law, and I'll explain why in a moment. But first, I need you to write this down carefully. Yeah. We're just waiting for Bruce. Yes, we're just waiting for Bruce. Go, Bruce. What's the Chinese for faster?
快一点.
Quite in?
Yeah.
Means faster?
Quite.
I'm sure that was someone in Batman, wasn't it?
No.
Quite in? Wasn't that like
快.
the guy in Batman who trains them?
No.
League of Assassins, no?
No.
You know Batman, don't you?
I don't really.
Oh, damn. Huh? What? What's going on? What's going on? German translations? No, I don't speak German, thank you.
German?
Yeah, you know German too?
I learned some.
Did you?
I
Huh?
learned some.
Does he?
Learned somewhat, but I forget.
Ah, very good, very good. Why did you learn German?
Because I want to go to a
Chinese
German.
German.
Good, interesting.
But German is too difficult.
It's very difficult.
In German, university is free.
Yeah, I know this. This is a good reason.
Yes, it's a good reason.
Okay, you got that now, Bruce?
Yeah.
You got it? Okay. Continuing.
Okay.
So, as I said, this is kind of a fake law, fake news. It's not always true. If it is true, then we say the resistor is ohmic. And if it's not true, then we say it's not ohmic. So when you think about it, that's not really a law, because a law should always be true. You know, it's like if I said Newton's law is F equals ma. If it's true, we call it a Newtonian mass, and if it's false, we call it a non-Newtonian mass. We don't do this, okay? Newton's law, F equals ma, is always true. But we kind of do that here. If it's true, we say, great, the law works, and it's an ohmic material. If it's false, we say the law doesn't work anyways, it was a non-ohmic material. You know, a law, but I don't really think it's a law. You need that word ohmic. If the law is true, then we call it an ohmic resistor. If it's false, we say it's not ohmic.
Teacher, Newton's law exists in quantum physics.
It does in a different form, though. It's not quite F equals ma, but there's a version of it in quantum mechanics. I think it's called Ehrenfest's theorem, but I don't remember its name.
Teacher, do you know a lot about
I studied
You studied
it for 3 years. Yeah. Yes. I studied it in 3rd year, 4th year, and on my master's as well. And I can tell you one thing about it. It is difficult.
Yeah, of course.
And what did you
Most difficult subject I've ever studied. Difficult.
Did you get any prize or something?
No. I was just happy that I passed it. So difficult. So difficult. Okay. Did you write that down?
Yeah.
Yep. Alright. Now, let's look at what the slope represents. So if I go back to this graph, what does the slope represent? Well, let's have a look and try and figure it out. So I have my graph. Here it is here. And we'll call that delta y, delta x. And this is I, and this is v. So the slope, which is change in y over change in x, that will be in like a current over a voltage. Now, if I look at this triangle VI-OR, you can see that OR is V over I. So the slope represents 1 over OR. Yeah. So in other words, what that means, when the slope is big, the OR is small. And when the slope is small, the OR is big. Okay? Is that okay? Yep. So that's what the slope represents. So actually, I think it's worth writing that down, that the gradient, the slope, is equal to 1 over OR for this graph. Yep. Yeah. Got that? Yeah. So, the slope, the gradient, is 1 over OR. I think you all wrote that down, yeah? Jerry?
Yes.
Okay. Right. In this question, it's the last example. We want to make this graph here. Let's see. Yeah, if you can just write the table down, and we'll make the graph together. So if you can just copy this table down. I think it's worth noting that this data is for what's called a filament lamp. Does anyone know what a filament lamp is?
I know film.
It's not related.
Ah.
Yeah. Filament lamp.
I know Philip.
You know Philip? Do you know lamp?
Made by film.
It's not a lamp made by a film, believe it or not. What is this? Yeah, but what the heck is that? Like,
Wire.
yeah, but where would you see it?
In the bulb.
But what type of bulb? Oh, not square ones. Oh, not square bulbs. Interesting. Yeah, but where would you see these bulbs?
In the shop.
Now, hang on. You're having a laugh now. Yeah, of course, in a lamp, not in a hat. Where would you see this lamp? There we go. So filament lamps, these are the lamps that you have on your study desk. And one thing you should know about these lamps on your study desk, you know, these lights on your desk, they get really hot. Really, really hot. Pretty quickly as well. That's important for this graph, because we're going to see now that this graph is not linear. Well, I mean, at first it might be, but later it won't be. Did you copy that table down? Yeah. Okay, let's make the graph together. So my voltage still... Move this out of the way. Come on. Away you go. Oops. And my voltage still goes from 10 to 1. But what's my current? Firstly? Yep. Four, 2 like this. Okay. Now I'll try and make that graph a little bit bigger to help you see. You notice that it's kind of hard to see, but it's not actually quite a straight line. What's happening for this graph, for this filament lamp, VI, at first it looks straight, but then it kind of starts to level off. So what does that tell me about the ore here? Big or small?
Small.
No,
Bigger.
big,
Bigger.
yeah.
Ah.
Ore becomes large here. Becomes larger. Yeah? That's important. Just so you know, for the exam, there's 3 of these graphs you must know. This is the second of the 3. Just to add the other one here, the previous graph was for a ohmic resistor. And that one was the nice one because that's just a straight line like that. You all have that one. This one here is for a filament lamp. Do you know a filament lamp? The one that's on your study desk. You know this lamp?
Ah, yes.
Sean, you don't know this lamp, do you? Hang on, I'll draw it for you. Yeah, don't laugh. I can draw this. Totally gonna nail this.
Lamp.
Told you, see?
Light.
Yeah.
Can change the word.
Sorry, it's English. And you know that this gets quite hot.
Yes.
Yeah. This is called a filament lamp. Can you add this graph to your notes? Oh goodness! Ah!
Oh, can't stop.
It's stuck now.
Dum.
Dum, 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 dum.
I bet for
Wow.
500.
Your computer
No.
is waiting for you.
Yes.
No.
Are you going to buy it for me for Christmas?
If you would like.
I think your 500 might be right.
Hey.
No.
Only 300.
Oh. Forget it. Just try and draw this, please. Yeah.
So in the result, you can't like that, does that mean that you haven't been put or more right?
Join the bus.
No, it's just you've increased the voltage running through it. So yeah, you're trying to turn up the brightness by increasing the voltage. I think what's happening for these things, as you try to, up the brightness, you're going to make the bulb run hotter. It's causing more resistance. These bulbs, I guess the brighter they shine, the hotter they should be. If this was very dim, It shouldn't really be that hot, but it'll also not be that bright. It'll be roughly ohmic. But we can see this one is non-ohmic.
Actually, now LED.
That's the next one. We're going to do that next. Yeah, yeah.
The lamp on my desk at home, the bulb, I don't know how to use it, but when I look at it, the filament has
Yeah, that's what normally happens when bulbs come to the end of their existence. The filament snaps. Yeah, that's normal. It didn't break. This is what happens when it burns out. Okay, did you draw that? Yep. Now, the other thing is extend the table to include the resistance. So let me just delete this ugly graph. So I'll just add in an extra one for resistance. What's the formula for resistance? V over I.
V of R. Yeah.
Yeah. Now, what do you notice is happening to the resistance here?
Increase.
Decrease.
Decrease? Yes, decrease. But remember, remember on the graph we go from small voltage to big voltage. So this is actually where we start on the graph. Voltage is 1. And as we increase the voltage, the R it gets bigger.
Yes.
Yeah, that's okay. Now, the last thing, which is the smallest and which is the biggest? 0.5 to 0.71. What happens if we run the current backwards? So if I just zoom out, where was my here? Oops, no. Here. What would happen if I just take this and flip it around? So it's like this. Well, not really too much. I mean, the voltage will become a minus,
Yes.
because it's backwards, and the A will become a minus as well because it's backwards. So if you were to look at this graph, the only difference would be out here.
Yeah.
No big deal. But in the exam, they do like you to include the negative part. So on your graph, if you could add that into the negative part. This one here, same deal, comes negative. So it would look like this, roughly. We have one more graph to do. I just want you to add these two into your current graphs, please. Can you add the extra part in, please? Yep. So, importantly, the resistor and the filament lamp, they don't really care about the direction. If you take the battery and turn it around, the only difference is your graph looks like this, minus minus. But is it really different? Not really. But the next one is interesting. What we're going to look at next is an LED light. You know LED?
Yes.
Yeah.
I think so. Now let's have a look at the IV graph for an LED light. I have the plot here. Now this is quite surprising because the direction does matter for an LED. If you reverse the battery, you don't simply get the same shape in the minus. You get a different shape. Now, before you draw this, let's just look at what's happening. As I increase the voltage, interestingly, what happens here? Does the resistance get bigger or smaller?
Smaller.
Smaller. Now, this is quite an interesting and useful property. As I increase the voltage, I get less resistance. Not more, I get less resistance. And if I run the voltage backwards, do I have a lot of resistance or a little resistance?
A lot.
A lot. So the LED really doesn't like the battery to be backwards, it has a lot of resistance if you try to push it through backwards. Until, what happens to the resistance? The resistance drops a lot. The resistance becomes really small. What's happening here with your light? Basically, it likes the current to go through one way, and if you have more current through it, it actually becomes a better conductor. The resistance drops if the voltage increases. But if you take the same LED and try to run the current through it backwards, you get a big resistance. It really doesn't want it to run backwards. And if you continue to increase the voltage, I think what happens here, something must break and the resistance drops and the current flows through with no problem. But I do wonder if at this point you've broken your LED. Something has kind of broken inside of it. So this graph is this interesting one because unlike the other two, the LED cares a lot about the direction. It cares a lot. So this is the last graph you would need to know for the exam. You need to know three different ones. The simple resistor, the filament lamp, and the LED. So you can add the LED. By the way, for this example, this point here, when the resistance drops, that's 0.7 volts. You don't need to know that, but just so you know, for LEDs, around about 1 volt is when the resistance becomes really small. Don't worry about all the names, it's the shape that I care about. Well, not actually, nothing's equal to infinity. I'm just trying to say it's quite large. Effectively, it doesn't really want to allow the current in backwards. But I mean, of course, if you put a voltage high enough, you can do anything you want, just push on through. But it tries not to allow the current to flow backwards. Yeah? No, it's the shape I want you to draw. Did you draw the shape?
Yeah, sure.
The shape and LED light on the top. Yes? You'd studied this before? Got that? Yeah? I'll say it again, it is actually very important for LEDs that their resistance decreases as you increase the voltage. This makes them actually quite useful for electronics, laptops, computers, iPhones. Because you know that your phone gets hot when you use it, your laptop gets hot, and you don't really want the resistance to increase, because then that wastes the battery. Yeah. So it's better if your resistance can actually decrease as it's left on and there's more voltage running through it. So there's a whole part of physics that studies all of these materials. These are special materials in physics. I think they're called semiconductors. Yeah. Because they don't quite behave like a normal conductor, because they have this unusual property that the resistance decreases as you try to pass a higher voltage across it. It's quite interesting. These materials were only really discovered around about the 1960s and 70s. So it's quite a new area, very important for electronics. So it will continue to be an important area in the future, these materials here. Yeah. Now, I didn't have a chance to put these questions on a page, so what you need to do, because I have them just at the end of the slide, if you can snap this on your phone, or I'll upload it to YouTube. It'll be at the end of the video. Basically, I just want you to make these two graphs and to answer these questions. And before you draw the graphs, I will point out I was being a little bit sneaky here because I said this one's in milliamps.
Oh.
Yeah? Like Paul was beside it, like physics.
I don't want it.
Not like what?
No, if I take a picture, I guess the rainbow.
What are you saying?
I guess the rainbow.
Yeah.
Is that crazy?
You're welcome. Oh,
Oh.
that's so difficult to read. The colours are so distracting.
Yeah, that's why I said rainbow.
What do you watch the video?
Yeah, I'll upload the video. We upload it in 5 minutes.
Yeah, but because you know what?